Hello, this is Szewczyk from DuPont Nomex electrical infrastructure team, and I would like to spend this next half an hour talking about the applications of Nomex insulation in the power transformers and the benefits that can bring for the transformers and the performance. I will talk about the latest trends that we observe in the electrical industry and the impact on the transformers, whether distribution or power transformers. I will introduce the alternative insulation systems, including the high temperature insulation systems. I will also introduce the new type of insulating paper that we have. It's called Nomex 910, and this is the thermally upgraded paper enhanced with Aramid. And then I will talk about various applications. I will describe various examples of the applications for the Nomex-based insulation systems. So to start with the mega trends and the impact on the transformer technology. What we observe in the industry is definitely the growing interest in the renewable energy. It's not new, it's just getting mature, and we definitely see for many years the growing size of the wind farms going today offshore, and the big investments, big developments in that area. We also see the photovoltaic plants growing in size and getting more popular. This all has got impact on the electrical infrastructure associated with it and the power transformer specifications. Often it's associated with the energy storage systems together with the renewable systems, renewable generation systems. The second factor that we see as an important mega trend is the electrical transportation. Huge investments and huge developments towards the electrical vehicles, with millions of vehicles expected on our roads in the coming years. And again, electrical infrastructure needed for charging those vehicles and supporting the needs of the vehicles. It doesn't have to be limited to the vehicles only. We can see the interest in the aircraft electrification and also vessels. We know already the cases where electric vessels or the ferries are becoming more popular in certain regions. The next one, which I'm showing here on the slide, is the digital revolution, or basically the growth of data, which has to be stored in the large data centers, and this is also requiring the infrastructure and the new requirements for the power supply systems, including the emergency power supplies or the fire safety considerations. So these are the three main mega trends that I'm listing here, but we could also talk about the climatic changes or the urbanization requiring the transportation systems, the railway systems, etc. If we look at the specific requirements for the transformers, we can see the needs in the increased loading of the transformers. So the transformers that have certain capacity today, they are expected to be loaded more in the future, and that's why current specifications for the transformers require more overloading capability or higher rating within the same physical size of the transformers. The first part of the chart here, the blue part of the chart, refers to the distribution transformers, and it illustrates the various cases that we observe when talking to our customers and partners in the industry, where the pole type transformers may be required to have the power capacity increased from 200 kVA to 270, or from 630 to 1000 kVA. We see the situations where the kiosk substations, the compact kiosk substations in the urban areas, they must provide more space for the larger switchgear or for the more connections to be made, and the transformer must be made more compact to accommodate for that. we can see some developments for the compact sidewalk transformers, which are needed in the larger numbers in the city areas. So we see those requirements in the distribution transformers. The green part of the chart for the renewable generation systems indicates the transformers for the inverter connections in the photovoltaic systems. They need to have the improved reliability, more overloading or more adjustment to the current cycle loads expected in the photovoltaic system. So whether this refers to the photovoltaic systems or the battery storage associated to them, there are possibilities for optimizing the transformer design using the advanced insulation systems for better performance and better cost optimization. Of course, with the wind turbine transformers, there is a growing size of those, including the large transformers up to 15 MVA and 66 kilovolt class for the offshore applications. But there is a big demand for the replacement of the transformers in repowered systems where the older turbines are upgraded, and this might require the new turbines to be installed, or at least the components, the critical components of the turbines are replaced with the new ones. So sometimes the new transformers of larger power capacity are installed in the same confined space which was provided for the older, smaller transformer. The last part of the chart are the power transformers, and we can see the more need for the resilient transformers for mobile applications or fast deployable for the case of emergencies. But we can also see the need for more overloadable or multi-voltage transformers for the area station applications. So the more regular transformers, not for emergency applications, but more typical transformers providing versatility and interchangeability in the system, again to improve the possibility of moving the transformers from one location, or at least installing the transformers in multiple locations for limiting the number of spare transformers, or the possibility of quicker reaction to the situations in the network. We can also talk about the alternatives to the gas insulated transformers. For example, in underground substations, the solutions with alternative insulation systems can help in some installations here. So when talking about alternative insulation systems, we can talk about the conventional insulation systems and the high temperature insulation systems. The conventional materials typically used in the transformers, or traditionally used in the transformers, include the cellulose-based paper and board immersed in mineral oil, while the alternative insulation systems may include Aramid paper and pressboard. In this case, we could talk about DuPont Nomex, and they may be often combined with the ester liquids, whether synthetic or natural ester liquids. Out of Aramid paper and pressboard, all the or majority of the typical insulation components can be made, whether based on paper or pressboard, for satisfying the insulation needs in the distribution or power transformers. One new type of insulation is what we call Aramid enhanced thermally upgraded paper. We call it Nomex 910. It might be sometimes confusing with other grades of Nomex, which are 100% Aramid papers or pressboards, and they are normally rated for the class 180 degrees Celsius in the liquid immersed transformers. The Nomex 910 is lower thermal class because it's basically the thermally upgraded paper with just a small proportion of Nomex added to it for improving the performance after long-term exposure to the temperature. So normally the cellulose, when exposed to the temperature in the operating transformer, loses its mechanical strength due to the degradation of the cellulose change, which is the natural process. While when we add Nomex to it, the Nomex component would require much higher temperature for being degraded. Therefore, when we have that Aramid enhanced paper in the equipment, the paper would lose less mechanical strength as compared to other classic papers, and this would extend the life of insulation system. We could also say that such paper could be exposed to higher temperatures. So when we tested the material in mineral oil as compared to the thermally upgraded paper, we could observe that the normal operating temperature could be not 110 degrees Celsius like it is for the classic thermally upgraded paper, but it could be 10 degrees higher. It could be 120 degrees. In esters, that could be even higher. So in esters, we could get to the normal operating temperatures between 130 and 140 degrees Celsius in the extreme case. So this paper provides the improvement comparing to the thermally upgraded paper, and it might be in the ester liquids, but even in mineral oil, it already offers the improvement of the thermal performance and the life of the insulation system. And when we talk about the alternative insulation systems allowing higher operating temperature, we have those systems covered in the international standards, whether we talk about the IEC, and here is the standard 676 part 14, or the equivalent IEEE standard C57-154. These standards define the applicability and the construction of different insulation systems using the high temperature materials like Nomex, and they also provide the guidance on the temperature limits. So, for example, here we have the guidance for something called mixed hybrid insulation system, where we have a portion of the winding insulated with the Aramid insulation. This is the white part of the winding shown on the chart. Or we could have a hybrid insulation system, or what we could call full hybrid insulation system, where the entire winding, including the conductor insulation, the spacers, is insulated with Nomex, while the parts which are in the distance from the hot conductor could be insulated with the cellulose. And when looking at the broader overview of various insulation systems available, we could start from the conventional insulation system, and this is the sketch, or the charts are based on the typical disc winding power transformer, where the conductor is insulated with the cellulose paper, and the spacers and the end insulation system is based on the cellulose. If we go higher with the performance of the insulation system, we could talk about the new paper Nomex 910 used for the conductor insulation, which would provide some life extension and improved short time overload capability for the transformer. Then we could talk about more advanced systems like the hybrid systems mentioned on the previous slide. So that could be a mixed hybrid system or the full hybrid system. They already allow quite severe overload and also the weight and side reduction in the transformer. So whenever the space or the weight is a constraint, like in case of mobile transformers for emergency, these solutions of hybrid insulation systems, they are popular in that type of transformers. When we look at the combination of insulation system with ester liquid, ester could allow higher operating temperature for the liquid, and then we may say that more insulation parts may be exposed to the higher temperature. So this sketch of the hybrid plus systems shows the Aramid insulation being extended to the barriers, to the winding cylinders, and even wet formed components which are located on the top of the winding. In extreme case, we could talk about the full high temperature insulation system, where the entire top part of the insulation system, including the end insulation or the clamping plates, could be insulated with Nomex. The bottom of the chart shows examples of those various insulation parts made with Nomex insulation material. And then moving to the examples of the applications for the alternative insulation system. One example is presented here. This is for the underground submersible transformers and the distribution substations. This is based on the concept, the historical concept of the compactness enabled by the high temperature insulation system based on Nomex. So in case of such substations, there is pretty much confined space for the transformer, limited space, and in case of need for the replacement, the new unit must fit the existing space in the existing installation. The problem becomes real if the utility needs a transformer of larger electrical size. So that's a real example. We were recently contacted by the customer from the utility who was looking for replacement of the distribution transformer with larger capacity, and then we started the discussion about using a high temperature insulation system in order to make sure that this transformer of larger power capacity, less sensitive to the periodic overloads that the grid is experiencing, this larger size transformer could fit in the same vault, and that then the solution with the Nomex insulation was considered. Another alternative for the underground submersible transformer could be a solution based on solid insulation distribution transformer, and this is the transformer without the liquid immersed insulation system. That's a transformer with the high temperature windings insulated with robust Nomex insulation and fully encapsulated in the compound, polymer compound. The result is the transformer that is insensitive to flooding or submersion in the water. So if we have the case of underground substation and this transformer becomes flooded after heavy rains, it should be able to survive those conditions. And additionally, this transformer offers a high level of the fire safety, because neither the winding insulation, the Aramid insulation, nor the polymer compound are flammable. So in case of urban installations, that would be a solution safe for the flooding, but also safe for the fire. And it could be also an alternative design which could be considered for those networks that are now being redesigned for eliminating the risk of the wildfires. Like we could hear that in California, major part of or significant part of the distribution grid will be buried underground to avoid the exposure to the forests and eliminating or reducing the risk of the fires. Such transformer, what we call SIDT, solid insulation distribution transformer in the underground vault, could be a good solution for those networks where the fire safety must be improved. And then moving to the photovoltaic systems, which I mentioned before, what is specific about them is the periodic loading and quite repetitive, and the loading cycle that may be evaluated based on the sun conditions in the area. What we know is that this repetitive loading cycle allows for the optimization of the transformer construction. This is an example of the typical bell curve in the photovoltaic systems when the maximum power capacity from the inverter system is available around noon. And this is the time when the transformer is really loaded, while starting from the morning and then later in the afternoon, the transformer can see less load, and eventually what is observed in the temperature records of the transformers, it is really only a peak loading in the transformer, and taking into consideration the inertia of the transformer weight for getting the temperature during the day, it is observed that the transformer, if it was designed to the maximum power provided from the inverter, it might not even get to the typical rated temperature. So there is a possibility of optimizing the transformer design to make sure that the power rating could be even derated, it could be even reduced comparing to the power rating output of the inverter, and with this the optimized cost of the transformer could be reduced. And if we consider that this peak load or the peak temperature for the short duration of the time during the day is the design factor, then the transformer design could be optimized if the insulation system would allow higher temperatures than conventional transformers. This is part of the study that was done by the KYTE Powertech in Ireland, and when this design analysis was done and the insulation life or the loss of life was calculated during such a typical loading period, it was observed that the application of the alternative insulation system, in this case Nomex 910, so the thermally upgraded paper enhanced with Aramid, so quite economical solution for the paper, when combined with mineral oil, it already offered a significant reduction of the insulation degradation with the same temperature, so with the same design, just different materials used for the winding insulation. It was significantly reduced. It significantly reduced the aging of the insulation. The aging was reduced by 60% when the temperatures were kept the same. So this shows that the design could be significantly optimized, and the actual either power rating of the transformer could be reduced, or the temperatures could be increased, meaning the cooling system of the transformer could be reduced in order to get closer to the more typical aging of the insulation system. The conclusions from the KYTE Powertech study showed that the cost optimization could be at least 8% as compared to the conventional insulation, and for some applications in the energy storage transformers that could be even higher. So that was important conclusion, that optimization of the transformer design based on the typical observed loading patterns for the photovoltaic transformers or the energy storage installations could really be the optimization would be possible, and the alternative insulation systems could be good enablers for cost optimization in such installations. While this was done for the step-up transformers, for the photovoltaic systems or the energy storage systems, the same could be possibly translated to the larger transformers, like the collector transformers in the larger photovoltaic systems. Then, when moving to the larger transformers, what is shown on the top of the slide is the typical mobile transformer for the emergency installations, the transformer which is fully assembled and filled with oil and ready to travel as such, together with the components of the substation and with its cooling system on the back of the trailer. So this is the solution which is quite common in North America today for the power utilities, while the newer developments include the growing size of such transformers. We do not call them mobiles anymore. We rather call them fast deployable, because the size of the transformer or the voltage rating may not allow transportation of the units fully assembled, like the one on the picture in the bottom right, which is the case from Spain, where the 250 MVA transformer was designed and built with the Nomex-based insulation system for achieving the great compactness for the transportation. So that was a spare unit to be installed in some critical locations in the grid to avoid keeping the spare transformers in every single substation throughout the state. And this transformer required disassembling for the transportation because it could not be transported with the 400 kilovolt bushings. And while the size of the transformer, after size and weight, after draining the oil and dismantling the bushings for the transportation, it was significantly smaller than conventional transformers. And we can see the comparison of this new 250 MVA unit as compared to the older 150 MVA units, which were much bigger and much more difficult for the transportation. So those compact solutions, what we call fast deployable transformers, could be a solution for the places where the transportation may be more difficult, where the road access may be more difficult, or where the road permits take time for arrangement and quick replacement of the transformers. Such a compact unit could be a solution for those places where access may be more difficult, or basically transportation of the transformer in the shorter time is needed. And while we are talking about a growing size of those transformers using high temperature insulation systems, this requires more and more developments and more characterization of the insulation systems and the specific components. So obviously the higher transformer, the larger transformer is required, and the higher voltage will be used. There is more and more precise characterization of the materials required. So we spend lots of time on working on those new components together with our partners for introducing the wet form of our Nomex board for making the end insulation components based on the wet forming process. We are working on increasing the size of the high density board for larger and larger components, which requires lots of characterization for the mechanical performance, for the dielectric performance of the new grades. If there is a need for the laminated board, like for the clamping plates, this requires thorough evaluation for the dielectric strength, not only for the press board itself, but also for the laminated board. So all kinds of analysis for the glue in terms of the partial discharge performance or in terms of chemical compatibility with the liquids, this is performed. So we are spending quite much effort these days on development of those various components so that the transformer designers and the transformer manufacturers could implement those in the larger and larger transformers. And here's an example of the applications produced by Siemens. On the left-hand side, we can see the project at Consolidated Edison in New York, where the trial installation of 3 units of 100 MVA was made, and this was with the record time of 30 hours of labor for installing and connecting those transformers to bypass the 300 MVA unit. In real case, the unit did not fail. It was just a trial installation, but the exercise showed that the installation or bypassing the 300 MVA transformer was available within those 30 hours of work. And in the top picture, we can see those actual 100 MVA units installed in the substation. So because of the reduced size and weight and modular construction of those transformers, it was possible to place them quickly in the substation, although there was no specific base prepared for those transformers. There was no concrete pads prepared or the space for those transformers in the arrangement of the substation, but due to the reduced size as compared to the conventional 100 MVA units, it was possible to place them in the substation and connect with the plug-in bushings and cable connections to bypass the existing 300 MVA unit. The solutions for the generator step-up transformers were also developed up to 400 kilovolt class. And we still continue those developments, and in this case with Siemens Energy and Consolidated Edison, there is a series of transformers already built and installed, and we continue those considerations for area station transformers where the units would have higher flexibility on the loading or the location for the installation of the transformers. So these transformers with the multi-voltage ratings and increased overload capability, they are enabled by use of alternative insulation systems. So various options for the hybrid insulation of the winding is practiced in those transformers successfully, and more projects are realized with that concept. So this fast deployment of the compact transformers is becoming real, and in case of Consolidated Edison, it becomes a kind of standard solution these days for the specification of the new transformers. Together with the alternative insulation system, when talking about the solid insulation, these transformers use the ester liquids for the fire and environmental protection. So these are kind of state-of-the-art transformers today, and we are proud we can contribute with our materials to those developments in New York. And to conclude the presentation, what I said at the beginning, we see those slightly changing needs in the transformer specification, in the requirements, and they could be a challenge to modern transformers, but we are happy to offer some solutions which can be helpful in overcoming those challenges. While Nomex insulation was historically used in very special applications, now it's still seen as the enabler in the new developments, and helps the designers to make high performance transformers for different applications, whether small transformers or the large transformers. And sometimes it may require the high temperature Aramid insulation, which is our let's say traditional product, although we developed the new options for it with the different size of the press board or different grades of the Aramid papers. And then the alternative solution could be the thermally upgraded paper, which is enhanced with Aramid, which is much more economical solution with not the same high-end performance, with kind of medium temperature performance, but also offering specific benefits to the transformer design. So sometimes the critical part of the new transformer development is its compactness and better mobility. Sometimes it may be the cost optimization. In both cases, the design options exist for improving the performance of the transformer, and the concepts, as mentioned already, apply to both distribution and power transformers, and various different issues or the new requirements may be coming from different end users, different power utilities, or the industrial users. So thank you for listening. Thank you for your attention. If there are any questions, feel free to send me an email, which is indicated on the screen, and I would be happy to answer those questions if only I will be able to find the proper and satisfactory answer. Thank you very much. And during that presentation given originally on on the webinar, I got some questions, and I will try to address the 3 of them. First question was, what do I think about the thermally upgraded paper improvement by esters? That's a important question and definitely popular topic at the industry. There are numbers of studies showing the improvement of cellulose by the ester due to the water extraction from the cellulose and extending the life. We also confirmed some of this phenomena with our paper Nomex 910, where the performance in ester is thermal performance in ester, or the aging based degradation is reduced with the ester. The only thing which probably industry must address better is the actual impact on the thermal class, because some studies are not complete or not following the standards for the complete evaluation of the insulation systems, and some studies, although a bit incomplete, they draw the conclusion for the actual improvement of the thermal performance, and the new thermal class is assigned on somehow incomplete aging studies. And what must be also a warning for the users or those who plan considering this improvement of the cellulose with ester is that not all the esters may give the same level of improvement. So our experience from various detailed tests and also from different publications that I could see is that different liquids may give different level of thermal improvement to the cellulose insulation. So it is important that whenever the conclusions are made for the improvement, they refer to specific liquid and they are not too generic for all the category of the ester liquids. So there may be different natural esters, they may be different synthetic esters, and it seems like thorough evaluations of the specific grade is required. The second question is about DGA analysis with those different insulation systems, or more specifically with the new paper Nomex 910. When Aramid insulation is used in the transformer, it does not give the same information on the aging or overheating as it is in case of cellulose, because Aramid insulation does not give the same aging markers like the cellulose insulation. We will not see the same hydrocarbons dissolved in the oil as it would be in case of degradation of the cellulose. So we would still see the degradation of the oil. So if there is an area of the insulation system which is overheated, it would give the information in the DGA analysis on those components coming from the hot oil. It would be less components coming from the Nomex, but in the hybrid insulation system where we have some components made with Aramid and some components made with cellulose, overheating of those cellulose components would still give the information on the overheating of some critical parts. If we talk about the Nomex 910, which is the cellulose paper combined with Aramid, it would give the information on overheating. So because there is still cellulose in that paper, it must be only remembered that there is less cellulose volume in that paper as compared to the typical thermally upgraded paper. So the volume of gases generated in case of overheating would be slightly less as compared to the 100% thermally upgraded paper. And the last third question is about if I'm a user of the transformer, how can I ensure that my transformer supplier would offer me a Nomex-based insulation system in the transformer? It's a very interesting question because sometimes the specifications for the transformers, even there are new requirements coming with the time, the specifications do not allow much flexibility to the transformer manufacturer to offer an alternative design, because either the materials are clearly specified in the historical specification, or the temperature limits do not allow any optimization using the higher class insulation system. So it may be important that for the new specifications or in specific projects, there is more flexibility given to transformer designer, or the reference is given to those standards for the high temperature insulation systems, which were listed before, shown before in the presentation, so that designer may have more flexibility, and the designer would do the optimization job and evaluate based on other limiting factors, or based on other requirements, whether related to the size limitation, the weight limitation, or the overloading requirements, or the lifetime calculations. The designer would be able to make the calculations, evaluate various insulation systems at the design stage, and then offer the optimal solution. So this a bit more relaxed flexibility to the designer would help in choosing the best insulation system for your transformer. Thank you very much again for your attention.